Study Section 9. Analysis of Variance, ANOVA. Introduction. The Studies section introduces you to another statistical method called Analysis of Variance, ANOVA. ANOVA can be one-way or factorial. The one-way ANOVA involves one independent variable, while the factorial ANOVA may be two or more independent variables having levels. Objectives. At the end of this study section, you should be able to 1. Explain when the use of ANOVA is appropriate, and 2. How to interpret ANOVA results. Pretext. What is the difference between one-way ANOVA and factorial ANOVA? Content. Analysis of variance ANOVA. Analysis of variance is a parametric statistical method used for determining whether significant difference exists in an experiment containing 3 or more sample means. As a statistical method, ANOVA divides variability, attributing portions of it to the effect of an independent variable, IV, on a dependent variable, DV. The assumptions underlying the use ANOVA include: A. The population where the samples were drawn from must be normally distributed. B. There should be random selection and random assignment of samples to experimental group. C. There should be equal variance on the groups. In this course, discussion will be based on one-way ANOVA for independent groups and for repeated measures. One-way ANOVA for independent groups. A one-way ANOVA or one-variable ANOVA for independent groups is a statistical method for analyzing the variation found within the various levels of a single independent variable. In other words, it is used to identify differences among sample means of an independent variable. A one-way ANOVA is used for an independent variable occurring at least 3 levels, and subjects are randomly selected and assigned into different groups. Example 9.1. A researcher wants to investigate the relative sociability scores of different major economics, sociology, and psychology in a university. The following scores were obtained on the sociability scale of 8 items from the students based on their major. The researcher then hypothesized H0. There will be significant effect of major on sociability. H1. Psychology major will be more sociable than economic and sociology majors. Table 9.1 below shows student scores on sociability scale. Steps in computation of a one-way ANOVA include: A. Compute the sums of each group by adding the scores to obtain the grand total summation x and the grand mean x bar for each group. B. Compute the sum of x squared summation x squared in bracket for each group. C. Add all the group sums to obtain the summation x. D. Add all the sum of squares summation x squared to obtain the summation x squared. You will arrive at the following for each major. The solutions are written below. You need to first calculate the correction term CT as it is written below. Compute the degree of freedom DF for each of the components SST, SSB, SSW. DFT is equal to total number of subjects minus 1. That is, n minus 1 is equal to 24 minus 1 is equal to 23. DFB is equal to number of levels stroke groups minus 1. That is equal to k minus 1 is equal to 3 minus 1 is equal to 2. DFW is equal to DFT minus DFB is equal to 23 minus 2 is equal to 21. Compute the mean square MS for each of the components. MST is equal to SST over DFT, not needed for the analysis. MSB is equal to SSB over DFB is equal to 110.33 over 2 is equal to 55.17. MSW is equal to SSW over DFW is equal to 63.5 over 21 is equal to 3.02. Compute the F ratio. F is equal to MSB over MSW is equal to 55.17 over 3.02 is equal to 18.27. You then need to present your result in a table. Table 9.2 showing a one-way ANOVA of effect of measures on sociability among students. Source: SS, DF, MS, FP. Between groups: 110.33. Within groups: 63.5. Total: 173.83. DF: between groups: 2. Within groups: 21. Total: 23. MS: between groups: 55.17. Within groups: 3.02. F: between groups: 18.27. P: between groups: less than 0.05. Interpretation of results. From the calculation, our F ratio is 18.27. You now consult the statistical table to determine either to reject or accept H0. The DFs for the numerator and denominator are 2 and 21 respectively. Using the DFs at one tail test of 0.05 level of significance, the critical value is 3.47. Since our calculated F ratio 18.27 in bracket is greater than the table value 3.47 in bracket, we accept H1 and reject H0. This suggests that measure of students have influence on the sociability. F into bracket 2.21 is equal to 18.27, P less than 0.05. The interpretation of this is that psychology measure X bar is equal to 7.25 in bracket are more sociable than economic X bar is equal to 2.25 in bracket, and sociology X bar is equal to 5.0 in bracket measures. This confirms the stated hypothesis. One-way ANOVA for repeated measures. In one-way ANOVA for repeated measures, each of the same subjects is exposed to different treatment or experimental situations. This type of one-way ANOVA is advantageous because it requires few numbers of subjects. However, there may be problem of carryover effect where the subject might be progressively more proficient at performing the tasks that might be due to learning and not the different experimental situation. The statistical assumptions underlying the one-way repeated measures ANOVA are: A. Those dependent variables are based on either a ratio or an interval scale of measurement. B. That the data collected within each level of the independent variable are independent of one another. C. That the distribution of the population from which the measures in each level of the four are drawn is assumed to be normal. D. There is homogeneity equal of variance. Example 9.2. An experiment was designed to test whether difference in the performance of machines, each experienced operators work on each of the machines for equal times. The number of units produced per machine was recorded for each operator. Test the hypothesis that there is a difference between the machines at significance levels of 0.05. The data collected for the experiment is as follows. Steps in computation of one-way ANOVA for repeated measure. A. Compute the sums for each treatment by adding the scores to obtain grand total summation X and the grand mean X bar for each treatment. B. Obtain the sum of the squared values summation S squared for each treatment. C. Add all the treatment sums to obtain the summation X. D. Add all the sum of squares summation S squared to obtain summation S squared. N is equal to 5 plus 5 plus 5 plus 5 is equal to 25. Obtain the correction term CT as shown below, where N is the total number of observations. Add the 5 scores recorded for each subject as follows: 21, 12, 17, 23, 15. Square each of the sums, add them together, and divide the result by the number of scores as follows. To obtain sum of square for subject, that is SS subject, subtract the correction term from the value obtained in the immediate previous stage. This is 325.6 minus 309.76 is equal to 15.84. To obtain the sum of squares error, that is SS error, subtract SS treat and the SS subject from the SST, that is SS error is equal to SST minus SS treat minus SS sub is equal to 84.24 minus 33.04 minus 15.04 is equal to 36.16. Compute the degrees of freedom DF for each of the components, that is SST, SS treat, SS sub, SS error. DFT is equal to number of measures minus 1, that is 25 minus 1 is equal to 24. DF treat is equal to total number of treatments given minus 1, that is 5 minus 1 is equal to 4. DF subject is equal to total number of subjects used minus 1, that is 5 minus 1 is equal to 4. DF error is equal to DFT minus DF treat minus DF subject, that is 24 minus 4 minus 4 is equal to 16. Compute the mean squares for each of the components. MST is equal to SST divided by DFT, not needed for analysis. MS treat is equal to SS treat divided by DF treat, that is 33.04 over 4 is equal to 8.26. MS sub is equal to SS sub over DF sub, that is 15.84 over 4 is equal to 3.96. MS error is equal to SS error divided by DF error, that is 36.16 over 4 is equal to 2.26. Compute the F ratio. F is equal to MS treat over MS error is equal to 8.26 over 2.26 is equal to 3.65. Now, you need to present your result in a table. Table 9.3 showing a one-way ANOVA of group difference in the machine output. Source, subject SS 15.84, DF subject 4, MS 3.96, F 3.65, P less than 0.05. Treatment SS 33.04, DF 4, MS 8.26. Source error SS 36.16, DF 16, MS 2.26. Total SS 85.04, DF 24. Interpretation. From the calculation, our F ratio is 3.65, You now consult the statistical table to determine either to reject or accept H0. The DFS for the numerator and denominator are 4 and 16 respectively. Using the DFs at one-tail test of 0.05 level of significance, the critical value is 3.01. Since our calculated F ratio 3.65 is greater than the table value 3.01, we accept H1 and reject H0. This suggests that there is a difference in performance among machines. F into bracket 4.16 is equal to 3.65. P is less than 0.05. A significant F value does not mean that the means are significantly different from each other until carried out in multiple comparison. However, since there is a significant difference, there is a need to compute a statistical procedure called multiple comparisons to know the extent of significant difference in the means. Summary. In the study section, efforts were made to explain and work out two types of one-way ANOVA with comprehensive examples. A one-way ANOVA is a one-variable statistical method but occurring at levels. This is the end of Psychology 319. Thanks for listening.